Hello, everyone. This is Azeotropic Distillation for Ethanol Dehydration by Matthew Bowman, Evan Lentz, and Patrick Rita. We went and found a research article online titled Dehydration of Ethanol Using Azeotropic Distillation with Isooctane. And we will be analyzing it, showing you the things that we've learned in our Thermo 2 class that are applicable to this article and why it's cool.
So hydrocarbons are used as fuel sources, as most people know. However, hydrocarbons by themselves are very inefficient and environmentally dangerous. So ethanol is added to these hydrocarbons to make them more efficient by oxygen addition. And so in order to add ethanol, usually dry ethanol is added to the mixture, or that can be cost ineffective and cost more money or energy to produce, thereby using and manipulating vapor liquid equilibrium in the azeotropic levels. You can add ethanol and water azeotrope mixtures into isooctane in order to make it a better fuel system and removing water in quick and easy steps. So these are the fugacity questions we've used in class. At the top, we have our azeotrope conditions, and that leads to pressure equals gamma A times PA sat. And at the other process conditions, we have the full entire fugacity balance.
So, as Patrick was saying about the azeotropic system, initially that feed stream of ethanol and water is easy to create as an azeotrope just by fermenting organic matter. And so what happens is you take that feed stream and you combine it with some pure isooctane and send both of those into a distiller as a tertiary mixture. And now, just because of how vapor equilibrium works, it's going to separate itself into a vapor and liquid phase. That vapor phase can be siphoned off, cooled down into a liquid, sent into a decanter, where just based on density alone, because as you can see, water is the most dense out of these three, it's able to separate the water out, and then the resulting liquid is sent back into the distillation column, where it's the vapor is once again siphoned off and sent through. This can be run as either a batch or a feed process. In this case, I'm talking about as a batch, where over time, the amount of water in the bottom's product is slowly decreased, and eventually you have a mixture at the bottom where it's almost just isooctane and ethanol.
All right, and then here are the experimental results from the article. This first graph here on the left, labeled A, is the bottom's product composition as a function of the reboiler heat duty. As shown, when varying the heat duty of the reboiler, the weight fraction of the ethanol and isooctane do not vary very much. However, when looking at the water composition in the bottom products, the water composition does vary a decent bit with the heat duty. Increasing the heat duty will decrease the amount of water in the bottom products, which is desired. For the aqueous decant composition, when changing the reboiler heat duty, it does not change the weight fraction very much. It is mostly ethanol, then isooctane, then water. And then for the flow rates, the flow rate of the aqueous decant is much greater than the flow rate of the bottom's product, and they do not vary much with the change in the reboiler heat duty. And that's about it. Thank you very much.
Thermo is cool.